and welcome back. So I hope you still remember what we have covered in the last class. So let me just recap a little bit about what we have been doing since last week. So again, one very important thing that as a programmer that we do is conditional testing, right? When you write programs, you want to do what is called a conditional testing. Okay, conditional testing. What does that mean? Now, when you're writing any loops, and most of the times our programs consist of a many number of these loops, right? Because we want to automate the process, automate some routine processes, right? That's why we want to use the computers to help us automate those processes. Okay, and we use these loops, for loops, if loops, for loops, while loops, if else statements, right? So these are some of the conditional, some of the programming constructs, if you will, okay, that utilizes these loops or these conditional testing. All right. Now, so what is the one common factor, one thing that is common to all of these programming constructs? In all of these programming constructs, we do this conditional testing, right? All in one form or the other, you're testing if, for example, you're comparing A to the value of B, and then, if they are equal, if they are larger than or equal, less than or equal, you write your program accordingly, right? Again, going back to your if-else statements, going back to your for loops, all of the time you're basically comparing a value to another value, and based on the comparison, you're performing a sequence of instructions. Okay, so that's one aspect. Now the question is, how does that relate? What you're writing as a program at the high level, how does that relate to what's happening at the ground level within the hardware itself, right? And to enable the connection, to enable the performance or the execution of these loops, we need what are called a single bit indicators called flags, right? So in the last week, we introduced the concept of flags, okay? And the other question that we wanted to answer was, we have designed as part of your arithmetic design, arithmetic operations, we have designed what is called an arithmetic adder, like, or a binary adder / subtractor, right? Now, the question to be asked is, can I use the same piece of hardware? We already know we can use it for addition operations, we can use it for subtraction operations. Now, what about signed number operations and unsigned number operations? Can I use the same hardware to perform both signed operations and unsigned operations? Now, again, from the perspective of the computer itself, okay, it can only see zeros and ones. It does not see beyond that. It does not assign any value to those numbers. It is you as the programmer who is assigning value to those numbers. If you're working with data, it is you as the programmer who is assigning value to those data. As far as the computer is concerned, as far as the hardware is concerned, it's just zeros and ones going through your system, going through your adder / subtractor, and it's outputting the result, right? Now, when it comes time to evaluate the result, it is you as the programmer who has to make the decision, and you have to convey that decision making to the hardware in whatever way possible. Okay, all right. So the question is, how can my hardware distinguish between, for example, I'm trying to compare two numbers A and B, right? Now, let's say my A is, let's take one example, 1001. B is 0101. Okay, I have two numbers, and if I pass those two numbers to the hardware, it just sees them as is. It does not assign any value. But as a user, as a programmer, if I know that these values are unsigned, If I know that, for example, again, let's say that those values correspond to some data. Okay, a data that corresponds to some, let's say, number of speeding tickets. Okay, number of speeding tickets. Of course, the number of speeding tickets has to be unsigned. It's positive. You cannot have a negative number of speeding tickets. So obviously, the data when I know that these data correspond to this particular, let's say in this example, a number of speeding tickets, I know that that's positive data. That's unsigned data, right? I don't have to worry about the sign. And just by looking at these numbers, because I know I'm the one working, assigning the value to those numbers, I know exactly which number is larger than which number, right? In this case, of course, my A is larger than B. Because I know that these are unsigned numbers, I know exactly A is larger than B. Okay. On the other hand, let's say I'm working with a different set of data, same numbers, but this time, I'm looking at this data as a credit card balance. Credit card balance. Now, in this case, my balances can be negative, right? So when I'm considering these numbers as credit card balances, then I have to assume that these can be unsigned. These are signed numbers because my balances can be negative. And when I do this, when I look at them as signed numbers, right, then obviously I can say that in this case, my interpretation changes. When I'm trying to compare between A and B in this particular example, my comparison will be very different. Different, right? In this case, my A is this holds for unsigned numbers. For the same set of numbers, this holds for unsigned numbers. However, when I'm considering these as signed numbers, then my interpretation changes, and my A in this case is less than B because now I'm looking at them as signed numbers. When I look at them as signed numbers, my A is negative because I'm looking at the most significant bit. The A is negative, B is positive, then obviously A is less than B. So the interpretation, the way I interpret these numbers changes the outcome, as you can see here. Now, when I'm trying to write a program which says, okay, compare, or let's say if A is larger than B, do certain set of expressions or certain set of instructions. How do we let the computer know at the hardware level that, hey, this time look at these as unsigned numbers, or at a different instance or a different part of the code, hey, this time my A and B are signed numbers. How do I communicate that information to the hardware? That's one question that we need to ask. Okay. All right. So now in the last class, we set out to defining various different flags. Okay. And we were successful in defining two different flags. One was the Z flag that indicates that, again, one single bit indicator that indicates if the result of an operation produces all zeros as my output from the adder, right? It could be an addition operation, it could be a subtraction operation. Irrespective of that, if my answer is all zeros, if my S zeros to S whatever S n minus ones are all zeros for an n-bit adder, my Z flag is set. Otherwise, it's not set. That's how we defined Z flag, and that's how we realized the Z flag. Okay, by using a NOR gate, putting all those outputs, the sums through the NOR gate, and calling that output of the NOR gate to be the Z flag. That's how we got the Z flag. Okay, and we also defined what is called the C flag in the last class. Okay, assuming for now that when I'm working with unsigned numbers, how do I compare between A and B as unsigned numbers? A and B, unsigned. So we define a new flag called the C flag. That is derived, C flag, derived from the C out, derived from the carry out of the adder, from the carry out. I'm saying derived because C flag is not really equal to C out, right? under all circumstances. C flag is not equal to C out. It's equal to C out under some circumstances, right? Because the way we define C flag, right? If A is less than B, I wanted my C flag to indicate when I'm doing A minus B operation here. If A is less than B, I want my C flag to be set. Again, indicating that I have to borrow. So I'm looking at my C flag here as an imaginary borrow, right? So I'm performing A minus B operation. A is less than B. That means my B has to borrow from an imaginary borrow, from this imaginary borrow C flag. Okay, so that's why my C flag is set, indicating that A is less than B. And I'm subtracting operations. If my C flag is 0, that indicates that A is larger than B. And the way we have derived it from the C out was because we also wanted to use the C flag for addition operations as well, in which case, okay, so C flag is not equal to C out for subtraction. And we wanted C flag to be equal to C out during the addition operations, because I wanted to use C flag also as an overflow flag, right? C flag, so C flag equal to C out for addition. And the way I can do that, in one case I want to invert my C out, in one case I don't want to invert C out during the addition operation, during subtraction operation I want to invert it. So the way that we have realized C out was using this XOR gate between my C out and the control input, which determines if my adder / subtractor is configured as an adder or a subtractor. Again, the control input with 0 indicates that I'm configuring this as an adder, in which case my C flag is basically equal to my C out. When I'm doing the subtraction operations, my control input is 1, in which case my C flag is the inverted version of C out, and it works out very well, exactly how we defined how we want it to work, right? Okay, so this is what we have accomplished in the last class, and then we basically came up with all the possible conditions for conditional testing or checking between A and B. When I'm doing A minus B operation, I'm looking for A strictly larger than B, A larger than or equal to B, A less than B, A less than or equal to B. So we have checked for all these conditions. We derived expressions as functions of flags, okay, to check for each of these conditions. Now when I'm writing a program, okay, when I'm doing, compare between A and B, at the hardware level, I'm looking for those conditions to satisfy. If those conditions are satisfied, those logical expressions between my C flag and my Z flag, remember it was a function of C flag and Z flag to test for each of these conditions. If my logical expression is satisfied, then that condition is that particular instruction is satisfied, and it will go into that into the subsequent set of instructions. Okay. We'll look at some examples of a program later on. Okay, that will actually clarify many things. But this is what this is where we stand right now. This is what has been accomplished in the last class. All right. Now let me take a pause and let me see if you have any questions on this content that we have covered so far. All right. And then we'll move forward in this class. We'll move forward with the second aspect of the flags. That means, we have done for the unsigned. How does that change for the signed? Let's say if I'm trying to compare between A and B numbers, in which case my A and B are signed, how do I compare between them? We have already seen in the last class that I cannot use my C flag anymore. This works only for if my A and B are unsigned. I can use my C flag and Z flag and base my comparison on functions of C flag and Z flag. For signed operations, we have already looked at an example in the last class where I cannot simply rely on C flag anymore. Okay. Now, any questions on this so far? Are you with me until this point? Okay, no questions. Then let's move on with the signed conditional testing. Again, we are not done with that yet. Let's again go back to our adders, our comparator. In this case, basically you have your adder circuit. That is also, we are adding additional functionality to your adder, to your arithmetic unit. Not only to just simply perform additions and subtraction operations, but also comparison operations, right? You can actually do the conditional testing using the same piece of hardware. Just by adding some few additional gates to it, we are able to, improve the functionality of this device. So now that's your adder / subtractor. That's your Cin, which is your, let me call it Cin here, which is your control input that specifies how we have configured it. So that's your A input 0 to 7. Let's say again, let's be consistent. We're working with 8-bit adder for now. Again, I could have just said A to 0 to 15 to make it into a 16-bit adder. It doesn't really matter here. Then you have B's going through an XOR gate. That's your B's 0 to 7. And that's your control input. Okay. You have S7, S6, S5, S4, S3, S2, S1, S0. Those are your sums coming out of the adder. And we get our 0 flag. That's your 0 flag, the output of this NOR gate. Okay, that's your 0 flag. The C flag is the C out. So that's your C out. The carry out coming out of the adder. We use the XOR gate to form your C flag. The other input to the XOR gate was your control input. Okay, so that's your C flag, and that's it. So that's that. And then we also defined what is called the sign flag in the last class. The sign flag, which we designate this as N with the letter N. So which is basically your S7, because that's your most significant bit of the result, and your sign bit is the most significant bit. So now that's your sign flag, which we call this the N flag. And for signed operations, I can now, because now I'm working with signed operations where the sign actually makes sense, I can start using my N flag to compare the magnitude between A and B. For example, let's say A is +2, B is -3. Okay. Let's again, for simplicity, let's focus on 4-bit numbers. So +2 is represented as 0, 0, 1, 0. -3 would be what? Again, +3 would be 0, 0, 1, 1. That means -3 would be the 2's complement of that, right? This will be 1, 0, 1, 0. That will be 0, 1, 0, 1. Oh, sorry, wait a minute. What did I do? That's not right. That'll be 1.
Wouldn't it be 1, 1, 0, 1?
That's right, 1, 1, 0, 1. It's negative, right? I have to get an MSB of 1. So that's -3. Okay. Now, can I rely on my N flag to make a decision between A and B? Let's say I want to want to write a program, and one of the statement is compare between A and B, which case in the hardware I'm doing an A minus B operation that tells the hardware to first, hey, do this A minus B operation first, and then look at the N flag. And look at the N flag. So what is A minus B operation here? My A is 0, 0, 1, 0. You're adding to that, the way this adder works, you're adding to that the 2's complement of B, which is 1, 1, 0, 0. And I get 1, 1 plus 1 is 0, 1, 0. That's a positive answer. Or in other words, my N flag is set. I'm sorry, my N flag is 0. That indicates that this is a positive answer. I can directly say here, A is A between A and B, A is plus 2, B is negative 3, my A is larger than B simply by looking at, because I know that these are signed numbers, in this case, A is positive, B is negative, I can simply say that, but I can also do this, I can also let the hardware do this, go through these steps, A minus B operation. I look at the N flag, which is the most significant bit, is set. That means the A minus B operation gave me a value that was larger than 0, which makes sense, right? If A is larger than B, A minus B should give me a value larger than 0. And this is exactly what happened here. And to know that it's larger than 0, I just look at the most significant bit, which is 0, which is positive. So I'm done. I can use my N flag to make the decision. Okay. So simple. Looks like it's actually much more simpler than my unsigned operations. But wait a minute. We actually have some complications here. What happens, let's take another example just to make sure that this always works. Whenever you're coming up with a strategy, you need to make sure that your strategy should always work, under all circumstances. It did work under this circumstance, but would it always work under all circumstances, right? So let's say my A in this case, let's take 2, 0, 0, 1, 0, which is positive 2. B, let's take that as 0, 0, 0, 1, 1, 1, 1, 1, 1, which is plus 7. Let's actually take minus 7. Minus 7 will be, again, plus 7, remember, is 0, 0, 1, 1, 1. That means my minus 7 will be negative of that. Take the 2's complement, so that will be 1, 0, 0, 1, 1, 0, 0, 1. That's negative 7. Okay. Now, because I know these are signed, I can tell directly by looking at these numbers that A is larger than B, right? There's no doubt about that because A is positive, B is negative, A is larger than B. But if I let the hardware do the decision, what does that do? Again, I'm trying to compare between A and B. So at the hardware level, I'm doing A minus B operation first and checking for the N flag. What do you expect for the N flag to be? I should expect that when I do A minus B operation, my N flag should be 0, right? Because A is larger than 0. A is larger than B. So let's see if that's indeed the case. So I do that, 0, 0, 1, 0. Adding to that, the 2's complement of B, right? A minus B, 2's complement of B, which is 1, 1, 1, 0. I add these two numbers together. So I have 1. 1 plus 1 is 1, 0. 1, 0, 1. I get this answer. What is my most significant bit? My N flag is set. In this case. Right? That's my N flag. That's how I define my N flag, the most significant bit. I expected my N flag to be 0 here because my A is larger than B. A minus B should have given me an answer larger than 0. However, in this particular example, my N flag is set. So what could be happening here? What's Why the discrepancy here? Seemed like a pretty straightforward thing. Can you identify what happened here? Yeah, that's correct. When I'm doing this operation, a minus b operation, that means I'm trying to do plus 2 minus or minus 7, right? The answer I got was plus 9. It should have been positive 9. When I'm working with 4 bits, can I represent plus 9 within the 4 bits? My range, yeah. Within 4 bits, no, I cannot represent within 4 bits, right? Because my range of numbers or signed numbers for 4 bits goes as minus 8 on the positive end to 0 to plus 7. That's the maximum. So plus 7 is the maximum positive number I can represent in 4 bits. I cannot go beyond that range. If I had an additional bit, fifth bit, I would have gotten the right answer. I mean, so even though this answer looks like a negative answer, it's just because we are not having that additional bit to accommodate the entire answer with the correct sign. I hope that makes sense, right? So what we are looking at is essentially a situation where we are having an overflow condition, right? Overflow. So I'm getting an answer that cannot really fit in the existing limited size of my memory. Because in this case, I cannot arbitrarily change the bit size of my adder, right? Because once I make my adder, the number of bits that it can output is fixed. I cannot do anything about that. So what we can do though is to check for the overflow condition. Otherwise, we'll be in a big mess. Whenever we have the overflow and when I'm just relying my decision only on the end flag, then my entire program will be messed up. Entire instructions will be messed up. To avoid that, I need to also check for the overflow condition, when the overflow condition actually occurs. Okay. And then at the combination of N flag, and let me call the overflow flag as the V flag, which indicates every time my overflow condition is set, that my V flag is set. So by looking at both of these flags, I may be able to come up with a more accurate decision when I'm trying to compare two signed numbers. Okay. So now let's look at the V flag. But before we do that, okay, now assume that every time we have an overflow, my V flag is set. Let's not worry at this time. Of course, we're going to talk about how we can actually realize that flag. But at this time, let's not worry about how we are realizing that flag. Let's say we have come up with some strategy to come up with that overflow flag. Okay, so we have that flag somewhere here. So every time we have an overflow, then that flag is set. So how do I come up with the rules now? Okay, so let's look at that. Or maybe we can just go ahead with the overflow flag. Let's actually define the overflow flag and then we can come up with the rules. So that makes more appropriate now. Okay, so let's define the overflow flag. Let's look at a strategy to actually construct an overflow flag for overflow testing. Okay, so how do we test for overflow? Now, when does overflow occur? Let's start with that fundamental question. When do we, let's say I'm working with 4 bits, and we have already seen that the range of numbers I can represent is -8 to 0 to +7, right? So that's the range of numbers I can represent in 4 bits. Okay. Now, when is the possibility of an overflow? When can we actually expect an overflow to occur? Let's say I take a positive number from this range and to that I add a negative number to that number, will that ever give me an overflow? I take any positive number from that, to that I'm adding a negative number from the same range, will that result in an overflow? You can try out some numbers and see under what circumstances, if it does result in an overflow, under what circumstances will it result in an overflow? What do you think? I'm taking a positive number from that range, to that positive number I'm adding a negative number. What do you think about the overflow condition? Will I have an overflow? Esteban, do you have any comments? What do you think? Okay, that's a no. How many of you think we will not have an overflow? Okay, that's fine. How many of you think we will not have an overflow? Okay, and the answer is correct. Yeah, we will not. So whenever I take a positive number and I add to that a negative number, we will never have an overflow, because whatever answer you will get, it will always be contained within the range. Right? Just like you can place those numbers on a number line, take any number on the positive side, any number on the negative side, add them together, the resulting answer will always be contained within that range on the number line. You can check it for yourself. So you will not have an overflow. So when do we have an overflow? So these are the possibilities. When I add a positive number to a positive number, there is a possibility of an overflow. It's not like we will always have an overflow. For example, when I'm adding 2 and 2, I get 4. That's within that range, no overflow there. But when I'm adding 7 to any other number, any other positive number, let's say 2, I get an overflow because that answer lies beyond the range. Yes, overflow happens when the answers are out of range. That's absolutely right. Likewise, when I'm adding two negative numbers, n plus n, let's say, again, p pos stands with positive number, n stands for negative numbers here. When I'm adding two negative numbers, again, a possibility of overflow, right? I can add -8 to -8, I get -16. Obviously, I cannot have -16 with 4 bits. I have an overflow condition, right? So again, negative plus negative can result in an overflow, not always, but it can result in an overflow. There is a possibility of an overflow. But when I add positive to negative, I can definitely be sure that there will not be any overflow, because the resulting answer would always be contained within that range. Okay. All right. So with that, so let's we don't have to worry about that. Now, how do we check for overflow? Now, when I add positive to positive numbers, I expect that I get a positive answer, right? Positive plus positive should give you a positive answer, which makes sense, right? Now, if that results in a negative answer, then that means I should have some kind of a flag. Hey, that's not right, right? Positive plus positive should result in positive. If my positive plus positive will result in a negative answer, that means, wait a minute, something is wrong. That means I have an overflow conditions happening here. That's an indication that, hey, I'm getting an overflow condition here. Okay. Of course, I need to derive some kind of a circuit to check for that, which we will do in a few minutes. Likewise, this is what is expected. If you get negative, that means I have an overflow condition. Likewise, if I have negative, I add negative number together, I expect it to be a negative answer. That's what is expected. If my negative plus negative results in a positive answer, that's not expected, right? That means that could be an overflow condition as well. All right. All right. So under what circumstances can we get this? Let's actually examine that. So positive plus positive getting us a negative answer. Negative plus negative getting us a positive answer. So let's examine that in detail. Under what circumstances do we actually get that? And then maybe from there, we'll be able to construct an overflow flag. So let's examine that. So let's say I'm trying to add two positive numbers together. When I say positive, that means my most significant bit is 0. And I really don't care about the rest of the bits, because my most significant bit of 0 represents that it's a positive number. And I'm adding another positive number to that. Again, the rest of the bits I'm not too worried about. I'm looking at the condition where when I'm adding a positive number to a positive number, I'm getting a negative answer. That means at the most significant bit position, I should be getting a 1. And then again, I'm not really worried about the rest of those. When I have such a situation, that means I have an overflow condition, because I'm not able to fit my answer in those limited number of bits. If I had one more extra bit, then that would have been enough to show the right answer. Okay. All right. Now, under what circumstances do I get a 1 there? How do I get a 1 there? When I'm adding two zeros, how do I get a 1 here? Any ideas there? Any suggestions? How do I get a 1 there? The carry. Very good. That means I'm adding whatever here, numbers, don't care what those numbers are, but if I do get a carry in here from that position as a 1, then I will get a 1. 1 plus 0 plus 0 is 1. Of course, my carry out from this most significant bit position is what? 0 here, right? Carry in should be a 1. In this case, my carry out is a 0. And in this particular situation, I will get a 1 on my most significant bit. Okay. So let me write that down here. So this will be carry in to the most MSB is a 1 here, and carry out of the MSB most significant bit is a 0, and I get a 1 there. And I'm adding two negative numbers. What about two positive? Two positive numbers. What about when I'm adding two negative numbers? When do I get an overflow? Again, when I say negative numbers, that means my most significant bit is a 1, followed by whatever numbers, whatever bits you have, I don't care. My most significant bit is a 1, followed by that. I'm adding these together, and I should get a 0 here, right? Because that's when I'm checking for the overflow. That means when I'm adding two negative numbers, I expect to get a negative answer, but here I'm getting a positive answer. Under what circumstances do I get a positive answer? You have the hint here already. So let's look at the carry into the most significant bit and carry out of the most significant bit. Carry into the most significant bit, carry out of the most significant bit. To get a 0 here, I need to make sure that carry in is a 0, right? If it's a 1, the carry into the most significant bit was a 1, then 1 plus 1 plus 1 would have given me a 1 on the most significant bit position here. So that has to be a 0. And then the carry out of the most significant bit position is a 1 here, right? Because 1 plus 1 plus 0 is 1, 0. The carry out is 1. In other words, in this particular situation, we have carry in to the most significant bit. Carry in, let me call that carry in, is a 0. Carry out of the most significant bit position is a 1. Okay. All right. So that's good. So you should be getting a hint already how to construct our Vflag, the overflow flag. Now let's also look at a condition. Let's also look at situations where I'm adding a positive number to a negative number, in which case I should not be getting overflow, right? So let's say my positive number is 0, 1, 0, 0. Oh, okay. Again, I don't worry about my, the most significant bit is what I'm worrying about right now. That's the positive number. I'm adding to that a negative number. Okay. Let's take example of, let's say, my carry in is a 1. So carry in, C in which case I'm adding 1 to 0 to 1. And what is my carry out then? 1 plus 1 is 0, 1. So my carry out is also 1. Right? I know that when I'm adding a positive number to a negative number, I should not be having an overflow. Okay. So in this case, I should not be having an overflow. My C in is 1, C out is also 1. Likewise, the other case is, again, I'm adding a positive number to a negative number. In this case, let's say my carry in is 0. So that's my C in. What's my C out? Also 0. Right? When I'm doing when I don't have, I know when I know that I don't have an overflow condition, my carry in and carry out are the same. Right? I've looked at all possible combinations, all possible conditions. Here they are the same. When I have an overflow condition, which happens when I'm adding two positive numbers together, two negative numbers together, I can see that my carry in and carry out are different. So how should I check for the overflow condition based on these? Can you suggest a method, or can you suggest a circuit, a simple circuit that I can use to check for the overflow condition now based on our observations? James? Can you think of an expression?
It would be, I guess it would be a AND gate for when they are the same,
Okay, AND gate between what and what?
possibly. Um, AND gate between, I don't know. You have carry out because they are the same.
Mm-hmm.
I'm not quite sure, but I know
Okay.
there's going to be some type of representation of it because there's a pattern there. So
you do see the pattern, right? Do you see the pattern there? If my carry in and carry outs are different, then I have an overflow. My carry in and carry outs are the same, I don't have an overflow. And Garrett, I just saw the text message, and indeed it's correct. So I can use an XOR gate. An XOR gate between what and what? I can use an XOR gate between carry in to the most significant bit, which is in this case, C out minus 1 position, right? The carry in from the B6 or the 6th bit to the 7th bit position, yeah? And the carry out, which is this carry out from the 7th bit. So I take an XOR gate between those two carry in and carry out, I get my Vflag based on our observation. Again, that's just our observation here. So now I can easily construct a Vflag. I hope that makes sense. Does it make sense? Any questions on this? So I'm assuming that it actually makes sense. So now we have derived our Vflag as well. So let's. So that's it. So that's the main set of flags that we need. So let's say this is my cout -1 position. Okay. And the way I will get my Vflag is by XORing those two couts, and that call that the Vflag. Now for your homework, you will be asked, and this is a required homework, so that means you have to do that homework. And if you don't do that, you'll be losing points on the homework. Okay. So you will be asked to simulate this and pass some numbers A and B. Assume again, because you are the one who's giving value to those numbers. Okay. And then look at once you pass different numbers, and then what answers you get for S's, how the flags get modified, and so on. So I would like you to be actually working through some examples here. Okay. All right. So that's good. So we have gotten that. So now, if I want to make a comparison between A and B, of course, in this case, A and B are signed, I need to be looking at both the N flag and the V flag. Now let's look at all different possibilities. So N, between N and B, and let's to get some kind of an idea about A minus B operation. Okay. Again, I look at all possible combinations between N and V, and look at what does that mean really in terms of the result of the A minus B operation. Okay. Now let's say N flag is 0 and V flag is 0. What does that indicate? What does that mean? N flag is 0. That means when I perform this A minus B operation, my N flag is 0. That means the answer that I obtained, the most significant bit of the answer is positive, or 0, or the answer is positive. V flag is 0. What does that mean? V flag is 0. That means my overflow flag is not set. That means whatever answer I got is the correct answer. So the result of this operation actually gave me a positive answer, which indicates that my A is larger than B. Because only when A is larger than B, I get a positive answer. What about this situation where I have N flag is 0, V flag is set? That means I'm performing A minus B operation. I get a positive answer, or an answer that looks positive because my most significant bit is positive. However, my overflow flag is set, which means that even though the answer looks positive, that really is not a positive answer. If I had one additional bit, then I would have, because I have the overflow flag set, if I had one more additional bit, I could have fit the entire answer along with the sign, correct sign, in those bits with the additional bit. Okay. So what that indicates is, even though my answer looks positive, because the overflow flag is set, my answer is actually negative. I'm not able to fit the entire number along with the sign in those fixed number of bits. So answer is negative. That means my A is less than B. Okay. What about this condition? In this case, again, my N is 1. That means the answer looks negative. My V flag is 0. That means I don't have an overflow. Right? That means whatever answer I got is the right answer along with the sign. So the correct sign, correct magnitude, whatever answer I got is the right answer. Okay. That means, and of course there's a negative answer, so that indicates that A is less than B. And finally we have N as 1 and B as 1. That means my n flag is set. That means the answer that I got looks negative. Okay. However, my overflow flag is set. That means if I had one additional bit, I would have shown with the right sign. Because I don't have that additional bit, my overflow flag is set. So the answer that I got is actually positive, but it looks negative because of that, because of the fixed number of bits. So in this case, my A is larger than B. Okay. Now, if I want to say what should I look if I want to say A is larger than B? What combination of flags, what combination between N and V should I be looking at to say A larger than B or A less than B? Do you see anything here? Okay, V XOR N, right? Because when V XOR N is 1 or true, I can say that A is less than B, right? 0, 1, 1, 0, 0, 0, 1, 1 gives me A larger than B. So in other words, I should be looking at V XOR N. If that is 1, that implies, that indicates that A is less than B. V exclusive OR N is 0 indicates A larger than B. Right? From here, from this table, I can make that call. All right, so that's the important thing done. That's the difficult thing done. Now it's a matter of doing exactly the same thing that we have done in the last class, bringing into picture the Vflag so that I can make all possible decisions now, right? So now we have to do not just these, A less than B or A larger than B, but I want to be more specific now in terms of what are the conditions to check for A larger than or equal to B, A larger than B, A larger than or equal to B, A less than B, A less than or equal to B. So I have to look for all these conditions. And again, if I want to check for the equal condition, then of course I need to also look at the Z flag. So it's a combination of N, V, and Z flag I should be looking at to make those decisions. And let's see what kind of what decisions we should be doing. Okay. All right. So now I'm going to draw another table now. In this case, I have N exclusive. I'm looking at the N exclusive OR V value and the Z flag value. After performing my A minus B operation, I'm looking at those values to make a decision now. Again, 0, 0, 0, 1, 1, 0, 1, 1. These are the possibilities, right? Okay. N exclusive OR V is 0. N exclusive OR V is 0. That shows that A is larger than B. And Z flag is 0. That means A is definitely larger than B. Or A is strictly larger than B. In this case. N exclusive OR V is 0. And but Z flag is set. And that happens, my Z flag is set. That means my A should be equal to B. Right? N exclusive OR 1 is 1. That means A is less than B. Z flag is 0. That means my A is strictly less than B. N exclusive OR V is 1 and Z flag is 1. And you will see that that particular condition now never happens. So I don't have to worry about that condition. The condition where your N exclusive OR V is 1 as well as the Z flag being 1. Okay. You can check for different numbers and you'll verify that doesn't happen. Okay. Now based on these, how do I say if A is strictly larger than B? If A to be strictly larger than B, I need to make sure that my Z flag is 0, right? In other words, I need to come up with a condition which constrains my Z flag to be 0. So I can say plus Z flag is 0. So when I use a condition like this, that means this condition is satisfied only when my Z flag is 0 as well as n exclusive or B is 0. That kind of places a constraint that both of these have to be 0 for A larger than B condition. Okay. What about A larger than or equal to B? So here I don't have to worry about Z flag. I don't have to place the constraint on Z flag. So I can just check for n exclusive or V to be a 0. Right? Wouldn't it be and Z flag? Oh, here and Z flag? I would say it's an or Z flag. If both have to be 0, because if it's and n exclusive or V and Z flag, this is also 0 when n exclusive or V is 1 and Z flag is 0. Or if this is 0 and this is 1. Right? Does that make sense? Got it? Okay. So yes, so this has to be true. So for an OR operation, for the result of the operation to be 0, then all of the individual terms have to be 0 for the OR operation to be 0. Okay. All right. What about the other conditions? For A, so I got that, I got this. For A strictly less than B, A strictly less than B, n exclusive or V to be a 1, n exclusive or V is a 1, because if n exclusive or V is 1, Z flag cannot be 1 at the same time. So that satisfies. And for A less than or equal to B, here either of these, if n exclusive or V or Z is 1, then this condition is satisfied, right? For A less than or equal to B, either this is 1 or this is 1, then this condition is satisfied, and that I can check for that condition. Okay. All right. So that's it. So now we are able to, compare between signed numbers. You can compare between unsigned numbers. We have derived the conditional testing, and it turns out that in an actual microcontroller, you actually have a register, a temporary memory location called a conditional code register. Also, in short, it's called CCR, conditional code register. Okay, so every time you're executing instructions, okay, as you're executing those instructions, the contents of these conditional code registers are changed continuously. Okay, and so actually now it's maybe a good time to actually look at the presentation again. But before that, let me take a quick pause here and see if you have any questions. Any other questions here? Because that concludes our discussion on conditional testing, on flags. Of course, you have other flags in an actual microcontroller, but let's not worry about them at this time. Hopefully that will be covered in your next version of this class, the higher version of this class. Any questions, clarifications on this so far? Once you actually implement this circuit, and once you start running examples through this, it will make much more sense. And I'm hoping that you'll actually enjoy doing that exercise. It's going to be a little bit more involved than your previous assignments, because you're actually simulating a circuit. So make sure that you don't wait until the last moment to start your assignment. You should start it right away. Any questions, concerns, any thoughts, comments? Now we need to go back to our question that we posed at the beginning of the class, right? How do we distinguish between signed operations and unsigned operations? How do I let the hardware know that at this moment of time, in this particular code fragment, I'm working with signed numbers? And the same code, it could be the same code. I may be working with a different set of data then I should let the hardware know that, hey, this time I'm working with unsigned numbers. Okay? So so Kamran, I've looked at your comment. It's close, very close. So the answer lies in how we formulate our instructions. Okay. So now that brings us to some examples of instruction codes, actual mnemonics, if you will. All right. So that's good. So we know everything. I hope you have taken this in your notes. So let me just take this out. Okay. Now the answer is, as you may already have seen, we are really looking at that's B, right? Okay. Well, that's okay. That was your Vflag. Okay. Now so when you're working with assembly language or when you're working with higher level language, you have to define what your variables are, right? That tells the computer what set of flags it should be looking at. Let's look at an piece of assembly code just to make it more understandable. Okay. So the way the program is written is this is how it actually works. So let's say this is your program memory. Let's say this is your program memory. Again, if you recall, the way we can imagine memory to be as basically a set of locations, right? Each location will have a unique address. So that's your address 1 or address 0, address 1, and so on. And each memory location can hold certain number of bits defined by the size of your memory, right? So you can imagine your memory to be organized in this fashion. Now, as I mentioned before, anything that goes into your device, whether it's data, whether it's program, whether it's text, everything has to be encoded as zeros and ones. So even your program has to be in terms of zeros and ones at the ground level, right? So you write your program, okay? So each of these memory location will hold your instruction codes, Now, when you're running the program, you're running one instruction at a time. That means you have a pointer that points to your memory location. So in your header, you basically specify that memory location in your program, where your program actually starts. And once the program is executed within the microcontroller, so that program counter basically points to subsequent memory location. The instructions are read, and the instructions are executed. Make sense? So you have a counter, program counter, that goes one memory location by memory location. Okay, so it goes sequentially. If I want to write, for example, like an if-else statement, how do I write it then in this way, in this particular organization? The way I would do that is I would use what is called the jump instructions or branch instruction. Let me call it branch instructions. What that means is a simple code could be something like this. Okay, I'll compare. Let's say this is at this particular location, I'm executing this particular code that says compare A and B, and then say branch, okay, branch if A is large. Of course, again, remember that, you have specific mnemonics in an assembly language code. You have specific mnemonics to encode each of these instructions. So that's branch if A is larger than B, and you specify the memory location. That's the memory location, the position of the memory location. So now what happens is, let's say it encounters this instruction here. When I'm doing this, when I'm trying to execute that instruction, what I'm really doing is I'm doing an A minus B operation and checking for the flags, okay? And if the flag condition is met, then I will branch. So instead of executing the next instruction here, I will branch to the location that is pointed, that is specified at this location, in this memory location. And then I start executing the code starting from that location. If the instruction is not met, then I continue executing from this location. Okay. Does that make sense? The process, how this program actually works at the hardware level? Okay. So that's a branch instruction. So instead of going sequentially, if this condition is met, you basically jump to a different location that you specify at the core as part of the code. Okay. Now, as I mentioned here, when I'm doing this conditional testing here, this is where you specify what A and B are. The way you specify is by writing the right code. Okay. Now it's the time. Now we can actually look at the actual code. All right. Okay. So we have seen this in the last class, and as you can see here, right? You see that? Okay. So we have seen this. As you see here, that's your actual code. But when you write these instructions, right, in your program, the compiler basically converts those instructions into actual binary code. Of course, these are represented in hexadecimal, but these are actually binary. These are entered as binary numbers in the memory. Okay, and this is where your conditional code register is. So again, you have 8 flags. In this class, we have covered N, Z, and B and C flags. And when you execute each of these instructions, this kind of layout shows which flags are affected when you execute those instructions. Because in this case, for example, when I say A, B, A, which basically says A, add B to A, okay, A and B are if you can imagine them as some locations within the CPU, as registers, locations within the CPU. So when I'm doing that, so these are the flags that are being affected when I execute that instruction. Okay. Now when I say this blanks, that means those flags are not being affected. Here again, this is another instruction, add C to A instruction where my flags are affected. Each of these flags are affected. Okay. So that's what it means. That's how you read that instruction set summary. That's the instruction set for a HCS12 controller. Okay. All right. And we've already seen this. These are your compare operations. So let's say you're comparing A to the content in memory location M. Again, the operation that happens when you write this instruction is A minus M operation. That's what happens at the hardware level. Let's not worry about the addressing modes. You will study them in the next class. And then, as you can see here, when I'm doing that, my N, V, Z, and flags are all being affected because I'm performing A minus M operation, and all of these flags are being affected. Okay, so compare operations affects all of these flags. That means those flags are updated when you do that, when your microcontroller executes that code, okay, in the hardware. Now, you have certain set of instructions. You have branch instructions that we just mentioned about, but there is a difference. When I'm trying to work with A and B, in this case, as signed numbers, I have a different set of branch instructions. When I'm working with A and B as unsigned numbers, I have a different set of branch instructions I should use when I'm writing the code. And this is actually specified in this slide, as you can see here. For signed operations, so these are the instructions I should be writing. Branch let's not worry about here. So let's see. Branch if less than, branch if overflow or no overflow. In this case, branch if no overflow. That means you're checking for the Vflag. Branch if less than, so you're doing the compare operation. You do the compare operation which performs A minus B operation. And then if my numbers are signed, then I will be using BLT. In this case, at the hardware level, I'm looking for this particular conditions. GE, which is greater or equal. In this case, I'm basically looking at these conditions. Branch if less than or equal, I'm looking at these conditions and so on. But these are, again, remember that these are all the conditions that we derived in the class. So these are for signed operations. On the other hand, if I want to treat A and B as unsigned operations, so in the process of my code, here I would be writing, for example, if A and B are unsigned or signed, let's say, then I will say, branch if less than or equal and specify the memory location here. So in this case, it's basically looks at BLE, right? BLE. So it looks at the Z, N, and V flag. If this condition is set, it basically branches to the memory location I specified here. If my A and B are unsigned, then I would not be using BLE instruction here, but I will be using, let's say, BLS instruction, which specifies the microcontroller that, hey, I should be looking at C and Z flags now. Okay, so that's how your microcontroller distinguishes between signed and unsigned operations. I hope that makes sense. So in other words, you're looking at a different set of flags for signed operations. You're looking at a different set of flags for unsigned operations. So this is your conditional code register that basically exists as a temporary location, temporary memory location, if you will, that is within the CPU. Okay, and these are the different registers you have that are within the CPU that can hold 8 bits of data. In this case, A and B, X, Y. That's your stack pointer. That's your program counter. These are all the registers that are present within your CPU. And that's your conditional code register that we just saw. Each bit of this location stores one flag. For example, here you have the C flag, the N flag, the Z flag, the N flag, and so on. Again, you have other additional flags here that we don't have to worry about this time. Now here's a simple program just to illustrate that. So for example, here I'm comparing between A, whatever content is stored in A location and X location. Okay, so this is compare A to the memory location that is pointed to by the register X. So in this case, you're storing some content here in this index register, the address of a memory location, and then branch if not equal to, and you specify the next is nothing but an actual memory location. So if not equal to, then loop back to next. So now when I try to execute this instruction, I look at the flags, the Z flag, right? Branch if not equal. If Z flag is set, then of course I don't execute this. If Z flag is set, if not set, then I start executing. Then I loop again. I go back and loop here, right? Branch if not equal. If not equal, then I loop back here. Compare it to the next memory location. Branch if not equal, I again check for the Z flag, loop back, and so on. So that's how you run. That's a simple example of a assembly language code, just to give you a sense of taste of that language. And it's actually, so you have to work with a little differently than what you're accustomed to in the high level language, but it's actually fun doing that. Okay. All right, I know we are out of time. I hope that makes sense. I hope that makes at least conceptual sense at this time. To actually see the connection between high level language, low level language, what's really happening at the hardware level. So with that, let me stop my talk here, and then let me see if you have any questions, comments. Yes, I would be able to post. I'm sorry about that. Yeah, let me just do that today. I'll be posting both of these lectures online. If you don't have any other questions, then yep, we'll stop here, and I'll see you guys on Thursday.